IBESS, Water and Aquatic Food Production, Part 1, examines the hydrological cycle, the cycling of water on Earth, and this movie introduces the impact of people on the water cycle. The significant ideas are the hydrological cycle is a system of water flows and storages that may be disrupted by human activity. Secondly, the sun's energy drives these flows, and humans are impacting the flows of energy and matter both locally and globally. And last, and pay particular attention here, the ocean circulatory system, the ocean conveyor belt, influences the climate and global distribution of water as matter and energy. Here is an outline of the movies available in the Water and Aquatic Food Production Unit. Use this outline to find the movie you need for review. This movie is focused here. Here is a continuation of the outline of available movies for this unit. This is a big unit. Here is an image that you've seen before. This is the Earth as a closed system. Light, high-quality energy enters the system. The energy is transformed into chemical energy by photosynthesis and flows through the system as chemical energy as the energy moves through the food webs and then leaves the system as heat. The biogeochemical cycles, the chemical elements and compounds, they cycle within the system among living organisms and the physical environment. Here are the relevant IB syllabus statements for nutrient cycling that includes the water cycle. Describe the processes involving the transfer and transformation of water as it cycles within an ecosystem within the Earth's system. Construct and analyze flow diagrams of the water cycle. Here is a simplified diagram of the water cycle. You can see the transformations in blue and the transfers in red. But be careful. Be careful and thoughtful with precipitation, because precipitation, rainfall, is a transfer, not a transformation, but precipitation has been preceded by condensation, which is a transformation. Now we can see the magnitude of the flows as a function of the width of the arrows. Remember that groundwater recharge is slow. Groundwater is renewable, but inputs are slow, so groundwater must be managed carefully. Surface water, seen here, is a renewable resource. Here are two specific IB syllabus statements related to the water cycle. State that solar radiation drives the hydrological cycle. State that fresh water makes up only a small fraction, 2.6% by volume, of Earth's water storages. Here is another simplified image of the water cycle, showing the relative magnitudes of the flows as percentages. Given the size of the oceans all together on Earth, it should come as no surprise that the evaporation and condensation precipitation over the ocean would be quite large relative to the same processes over land. In one more simplified image of the water cycle, you can see the magnitude of the flows as rates times 1,000 cubic kilometers per year. Remember that precipitation flows represent condensation first, then precipitation following. Condensation is a transformation, a change of state, while precipitation is just a transfer, a change of location. This flow is runoff, rivers to ocean. This flow is the transfer of water vapor or gas or clouds as liquid from one location to another. This flow is known as advection. In this image, we can see a slightly more complicated view of the water cycle. I would like to bring to your attention evapotranspiration, the evaporation of water from leaves of trees as the plants bring up water from the ground through their root system. This is a transformation. As well, you can see water vapor being transported by the wind here, and this is known as advection, wind-blown movement. This would be a transfer of water vapor gas or cloud as liquid. Runoff, seen here, is what you might notice as stream, river, or flood condition. Runoff is a transfer, and without the impact of pollution, this would be clean water ready to drink. Groundwater originates from two processes: infiltration, where water on the ground surface enters the soil, right here, and then percolation, where water seeps or filters through the ground without any definite channel. Also keep in mind evaporation, a transformation of liquid to gas, and then condensation, also a transformation of water vapor, gas to liquid, and then precipitation, which is a transfer. Here is a list of the flows in the hydrological cycle labeled as T1 transfers or T2 transformations. The T1, T2 designation is my notation, not that of the IB. The IB expects you to know which flows are transfers and which are transformations. I'm going to let you study this slide on your own, except I will note that you do need to be aware of ocean currents, which are transfers. Use this image to locate all the flows of the hydrological cycle that I've previously mentioned. This image includes sublimation, which is a transformation of solid directly to gas, in other words, ice directly to vapor. This image does not show well advection, the wind-blown transfer of atmospheric water vapor. Here are the storages in the hydrological cycle. The units for storages in the water cycle would be mass or volume. No rates. I'll let you study this slide on your own. Use this diagram to locate all of the storages of the hydrological cycle that I've previously mentioned. The storages are noted in white color. There are organisms, oceans, lakes, rivers, groundwater, including aquifers, glaciers, ice caps, and the atmosphere. And don't forget the fundamental difference in storages and flows. Their respective measurements are different. Flows are rates, and storages are not. Here is a last image of the water cycle. Spend some time studying this image. It shows both infiltration and percolation and advection as three transfers, the detail of which you need to gain control. And here is runoff, streams and rivers perfectly clean without the impact of pollution. Keep this in mind. Water that precipitates to become runoff is perfectly clean water, ready to drink. Unfortunately, as water runs downhill into our cities, we change the quality of runoff. Ocean currents are related to the water cycle, though the currents flow within a single storage, within the ocean. Ocean currents move heat from warm equator regions to the poles. The ocean circulation systems are driven by differences in temperature and salinity, both of which influence water density. It is the difference in water density that drives the movement of the currents, serving to distribute heat and influencing local climate. The ocean conveyor belt is a large-scale movement of ocean water that serves to distribute heat from tropical regions to polar regions. You can see how water moves along the surface and then sinks due to density differences, then moves at depth only to resurface due to density differences. The flow of water within the ocean, known as ocean currents, is driven by differences in temperature and salinity, both of which influence water's density. As you can see, the ocean conveyor belt distributes heat, and it's referred to as the thermohaline circulation, temperature salinity circulation. This diagram displays the impact of ocean currents on local temperatures. The diagram displays mean surface temperature values as lines of a single temperature known as isotherms. These isotherms are for January, and again, I'm showing you this diagram to illustrate the importance of ocean currents in distributing heat. If you follow a single line, say 5 degrees C, you are following a certain temperature across the globe, and any location south of this isotherm is warmer than 5 degrees C, and any location north of this isotherm is colder than 5 degrees C. Keep this in mind. Let's start by looking at this image from just a distance, kind of step back, just to see the overall temperature pattern. Over land in January, isotherms dip to lower latitudes, indicating cold temperatures at relatively low latitudes in January. Over water in January, isotherms push up into higher latitudes, indicating warm temperatures at relatively higher latitudes. In January, at a given latitude, land is colder than the ocean, and this is because oceans are moving heat. But let's look closely to see the real power of ocean currents for distributing heat. Let's follow this isotherm here, 5 degrees C, 45 degrees Fahrenheit, from land over North America into the North Atlantic. Remember, all the isotherms that are north of this 5 degrees C line are colder, and all the isotherms that are south of this 5 degrees C are warmer. Now, look what we see when we follow this 5 degrees C isotherm. 5 degrees C temperatures extend far to the north, to high latitudes, where you would expect the temperature to be much less, much colder. These warm temperatures are pushing north. The North Atlantic Drift, also known as the Gulf Stream, brings warm water from equatorial regions to north latitudes. The United Kingdom and the west coast of Norway are dramatically warmed by this current that takes the warm water to the north. Similarly, the western coast of South America is cooled by the Humboldt current, bringing cold water from the South Pole to the equator. The western coast of Chile and Peru is cooled by this cold water moving north. Differences in water density drive the ocean circulation. Water density is influenced by both temperature and salinity. Again, notice how this relatively mild -1 degree C extends nearly to the Arctic Circle. The western coast of Europe, particularly Scandinavia, is significantly warmed by ocean currents carrying heat from lower latitudes. Here are the next IB syllabus statements. Describe the impact of human activities on surface runoff and infiltration, including agriculture, deforestation, and urbanization. Discuss human impact on the hydrological cycle. Now, human activities are having the following impact on the hydrological cycle. Here are the impacts. Humans are changing the rate of extraction. Thus, there's been a reduction of storages, reduction of river flow, and groundwater. Humans are redistributing water, moving surface water from one location to another using canals. As well, humans are slowing surface flow behind dams. Humans are changing the rates of evaporation, infiltration, and runoff through agricultural practices and deforestation. And humans are changing the quality of the runoff through pollution. Now, urbanization and increasing population numbers are putting pressure on water resources, exacerbating, making worse, all of the ways in which people interact with water. Agriculture has an impact on surface runoff and infiltration. Irrigation extracts water from rivers and spreads it out across the land. Now, as I present images of human impact on the hydrological cycle, I want you to be thinking, what's the impact? Is it extraction, a reduction of storages? Is it redistribution, canals or dams? Is it changing rates of evaporation, infiltration, and runoff? Or is it changing the quality of runoff, in other words, pollution? Or is it all of the above? Irrigation canals divert water from the river's channel and redistribute the water to locations that need more water. But be thinking, what's the impact? Is it increasing rates of extraction with a reduction of storages? Is it a redistribution of water through canals and dams? Is it changes in the rates of evaporation, infiltration, and runoff? Or is it influencing the quality of runoff? In other words, pollution. Or is it a combination of more than one? In some rivers, so much water is extracted that water no longer or rarely flows to the ocean. This is a photograph of the Colorado River in Mexico as it approaches its outlet with the ocean. Not much water is left. Irrigation flooding increases the evaporation of water into the atmosphere and increases the infiltration of water into the soil. Agriculture using surface and groundwater irrigation dramatically redistributes water. Surface water and groundwater storages are highly reduced as a result of irrigation in agriculture. Irrigation dramatically redistributes water. Groundwater storages are highly reduced as a result of irrigation in agriculture. And a lot of what was once groundwater now evaporates into the atmosphere. Urbanization has increased the demand for water in densely populated areas. This increases the amount of water being extracted and diverted from the original channels. Urbanization and increasing population sizes have increased the need for irrigation. Large populations need food, and the need for food has increased the demand for water. Dams have been built to provide the water, but dams have changed the course of rivers. Large volumes of water are now held behind dams. But I want you to be thinking, what's the impact? Is it increasing rates of extraction with a reduction of storages? Is it a redistribution of water in canals or with dams? Is it influencing rates of evaporation, infiltration, and runoff? Is it influencing the quality of runoff? Pollution. Deforestation reduces the infiltration of water into the soil because the water that falls on a deforested land runs off the land quickly. Deforestation reduces evapotranspiration. Less water is released to the atmosphere. Less water in the atmosphere means less precipitation. What's the impact of deforestation? Is it increasing rates of extraction with a reduction of storages? Is it a redistribution of water through canals and dams? Is it influencing rates of evaporation, infiltration, and runoff? Or is it influencing the quality of runoff, as in pollution? Deforestation reduces the infiltration of water into the soil. Water runs off the land quickly, and the erosion of soil increases. In the photo on the left, the burned forest results in rapid water runoff into the gully, increasing the rate at which the gully is eroded. Notice how water erosion has gouged the gully. Increased rates of runoff muddies rivers, resulting in an increased flow of sediment to where the rivers meet the oceans, seen here on the right. Deforestation decreases natural infiltration and increases runoff. Soil integrity weakens. Landslides are the result. Deforestation alters the quality of water runoff. Trees hold the soil, thus deforestation results in soil loss, an acceleration of erosion, as can be seen in this muddy river. In Thailand, deforestation has accompanied an increase in the population size along with urbanization. The political boundary of Thailand is apparent in the deforestation of the country. The political boundary, unlike that of Laos or Myanmar or Cambodia, Thailand's deforestation defines the entire country. Now, the world's population is 7.3 and growing. 51% of the world's population is now living in a city, and the percentage is growing. Both population growth and urbanization are putting pressure on water resources, increasing the demand in certain locations for fresh water. Urbanization alters runoff and infiltration of water into the ground. Urbanization prevents water from naturally infiltrating and percolating to become groundwater. Flooding is the result. Urbanization decreases infiltration and percolation and increases runoff, and flooding increases. Urbanization decreases infiltration and percolation and increases runoff. Urban flooding increases. Pollution alters the quality of surface runoff. People use the flow of rivers as a means to get rid of waste from their immediate environment. As a result, most surface water is no longer drinkable. And with urbanization comes sewage. Pollution, such as sewage, alters the quality of river runoff. People use the flow of rivers as a means to get rid of waste from their immediate environment. As a result, most surface water is not drinkable. Over the last 20 slides, I have presented these two IB syllabus statements. Describe the impact of human activities on surface runoff and infiltration, including agriculture, deforestation, and urbanization. Discuss human impact on the hydrological cycle. I have suggested that human activities are having the following impact on the hydrological cycle. We are changing the rates of extraction, thus there has been a reduction of storages, a reduction of river flow and groundwater. Humans are redistributing water, moving surface water from one location to another using canals. As well, humans are slowing surface flow behind dams. Humans are changing the rates of evaporation, infiltration, and runoff through agricultural practices and deforestation. And humans are changing the quality of runoff through pollution. Urbanization and increasing population numbers are putting pressure on water resources in very specific locations, making worse all of the ways in which people interact with water. Let's bring this movie to a close with a bit of review of water on Earth. Remember, the characteristics of the Earth's biomes are determined mostly by the presence or absence of water, as well as a prevailing temperature, as well as available light. Remember, rainfall varies by latitude. Equatorial regions receive the most rainfall, and polar regions receive the least on average. Regions 30 degrees north and 30 degrees south of the equator also receive very little rainfall. Now remember, the tricellular model of air circulation explains the distribution of precipitation. And if you're not sure about the tricellular model of air circulation as an influence on the distribution of biomes, please review Ecosystems 2, Part 6. This diagram displays evaporation versus precipitation at different latitudes. You can see that when evaporation is greater than precipitation, marked plus on this diagram, colored yellow, we would have deserts. In regions where precipitation is greater than evaporation, marked negative, purple, we would have rainforests. While precipitation is low in polar regions, so is evaporation due to cold temperatures. Thus, polar regions are negative slightly. There is slightly more precipitation than evaporation. But 30 degrees north and 30 degrees south of the equator are deserts, where evaporation is significantly greater than precipitation. Again, review your understanding of the tricellular model of air circulation to understand biome distribution. This is Ecosystem 2, Part 6. And that brings us to the end of IBESS, Water and Aquatic Food Production, Part 1.